In this video, we're going to show how the Galilean transformation equations can be derived from first principles. Suppose there are two coordinate systems named S1 and S2. The system S1 has three unit vectors named e sub x, e sub y, and e sub z. Similarly, system S2 has three unit vectors named e sub x prime, e sub y prime, and e sub z prime. The time coordinate for system S1 is t, whereas the time coordinate for system S2 is t prime. Systems S1 and S2 are coincident at t equals 0 equals t prime. With respect to system S1, system S2 is translating in the positive e sub y direction with a speed v. In this case, the speed v is equal to the absolute value of delta y divided by delta t. Also in this case, delta y is greater than 0, and we assume that delta t is greater than 0. From the perspective of system S1, system S2 appears to be traveling in the positive e sub y direction. If we assume that the standard equation of displacement equals velocity times time interval is valid for a case with no acceleration, then after a time interval delta t has elapsed, system S2 has translated a distance delta y in the positive e sub y direction according to system S1. So far we have considered the perspective of system S1, but there's also the perspective of system S2. We have already established that system S1 can track the motion of system S2. Therefore, system S1 can track the position of the origin of system S2. A reasonable assumption is that system S2 can track its own origin, just like system S1 can track its own origin. So even though system S2 is moving with respect to system S1, we have established that both systems can track the same element of system S2, namely the origin of system S2. The point I'm trying to make is that system S2 and system S1 can describe the same spatial location, which is the origin of system S2, with different numerical values. To be concrete, system S2 assigns 0, 0, 0 for the coordinates x prime, y prime, and z prime. This makes sense because an origin of a coordinate system is at 0, 0, 0. But for system S1, things are a little different. According to system S1, the coordinates of the origin of S2 at t equals delta t are 0, delta y, 0. In other words, for system S1, when t is equal to delta t, x is equal to 0, y is equal to delta y, and z is equal to 0. Here, x, y, and z are the spatial coordinates that S1 is using to describe the origin of system S2 at t equals delta t. In contrast, from the perspective of system S2, the origin of system S2 is described by x prime equals 0, y prime equals 0, and z prime equals 0. At this point, we don't concern ourselves with what t prime is equal to. All we need to realize is that y prime is not equal to y. They're offset by delta y. In particular, y prime is equal to y minus something. What is this something? We see that y prime is equal to 0, whereas y is equal to delta y. And the offset is by delta y. So we can say that y prime is equal to y minus delta y. And how did I know that y prime is equal to y minus delta y? Well, in this particular case, we have y prime equals 0 and y equals delta y. So if we want y prime to be equal to 0, then we need the right-hand side to be equal to 0 too. We know that y is equal to delta y, so in order to get 0 on the right-hand side, we need to subtract delta y. So that's why the right-hand side is y minus delta y. In this case, we have delta t greater than 0, And recall that the speed v is equal to the absolute value of delta y over delta t. Let's assume that the speed needs to be greater than 0, which we normally do. If delta t is greater than 0, then we can multiply both sides of the speed formula by delta t to get delta t times the speed v is equal to the absolute value of delta y. Now, if delta y is greater than 0, which is what we have in this case, then we actually can say that the absolute value of delta y is equal to delta y. So the absolute value isn't needed. And so the previous equation becomes delta t times the speed v equals delta y. And now we have an expression for delta y. So we can say that y prime is equal to y minus delta y, which is equal to y minus v delta t.